Welcome to ZKast, everyone. I'm ZS Caravallo from ZK Research, and I am joined today with Dave Salvator, Director of Accelerated Computing Products at NVIDIA. I'm excited about this. We're going to be talking about AI, of course, which is it's kind of a broad topic, but it's something certainly everyone's talking about. Dave, before we get into it, though, can you just give a quick intro on yourself and what you do at NVIDIA?
Sure. Yeah. Hi, Zay. It's good to be with you today. So here at NVIDIA, I work on a kind of a wide variety of things. I work quite a bit with our cloud partners, helping them bring our products to market and offering our technology and our platform as cloud instances on their platform. I also do a fair amount of work around our involvement with MLPerf and the ML Commons benchmarking consortium, and I think we'll talk a bit about that today. And then I do a fair amount of blogging and just writing about our technology and the innovations we're bringing to the market.
All right, and since you brought up ML Commons and MLPerf, let's start there. And so the results, there was some MLPerf inferencing results just released. Before we get into what the results were, can you talk about LLM inferencing, why it's hard? Maybe start with an LLM inferencing 101 and then talk about the challenges behind that.
Sure. So LLM is a large language model, right? And as the name implies, large language models are large. And so the first challenge you get into is that the models themselves have been growing at a very rapid rate. In addition to that, on more the training side, before you deploy it for inferencing, developers are trying a bunch of different approaches to find ways to make better LLMs, but also make them in a way that's cost effective to deploy. So they're looking at things like mixture of experts as an example. Another thing they're doing is they're running many more tokens through the network, sometimes smaller networks, to get results that are more on par with some of the larger networks. So that puts more work on the training side, but what the payoff for that is, if it works out, is the fact that when you go to deploy, you're deploying on a network that is essentially not as big, and so you can use either less infrastructure or can deploy a richer model, but you're able to deploy in a way that's more cost effective. So it poses kind of multiple challenges for organizations looking to take advantage of it. But the other interesting piece of LLMs is that a lot of the services being deployed, things like ChatGPT and other chatbot type services is one example, are expected to run in real time, which is to say that when you put in your question to a chatbot, you don't want to be waiting around for that answer. You want the answer to start coming in fairly quickly. And when it starts coming in, you want it to stream in at a rate that is definitely human readable and maybe even lets you read ahead or scan a little bit or skip a little bit. And so those are the things that go into making a great user experience for these applications. So, there's kind of multiple things that developers and infrastructure managers have to solve for when they go to deploy these models.
Yeah, that's it's interesting too, because if it is slower than you can read, it's incredibly frustrating.
Yes.
And even if it's just slightly ahead, it's the experience is just much better. So with MLPerf inferencing, though, why has that become such an important industry standard? Why, like, that's the benchmark today, and how did it become that?
Well, so MLPerf got its start about 6 years ago. It was created by a number of founding companies of the ML Commons consortium, including Google, NVIDIA, a number of universities, and a number of other industry companies who are really interested in AI. Industry standard benchmarks have been with us for decades and decades, and they're an incredibly important evaluation tool for companies looking to make big IT investment decisions, right? The thing that they do is they bring together companies in a way that they're all measured on the same work, and that the results are then reviewed by every other submitter, that these are peer-reviewed results, so that the results that ultimately publish have been vetted. And that's really important, that they be directly comparable and vetted, so that you're looking at numbers that are going to be solid numbers that you can actually look at and know, okay, these are numbers where I really have a sense of the relative performance of the different platforms. And ideally, if that benchmark's doing its job, it will also have a wide enough set of workloads, a diverse enough set of workloads that's doing a pretty good job of covering the industry it's trying to represent. And we think that MLPerf does a really good job on pretty much all those fronts. To wit, the most recent version of MLPerf inference has added an MOE, or mixture of experts workload, called Mixtral 8x7b, right? Which essentially is 8 experts. You can think of them as all working sort of together to solve different types of problems, One of the neat things that MOEs do is, of course, is that they let a single deployment solve a wider set of problems because each expert can handle kind of a different area depending on the nature of the question or the query coming in.
Yeah, and so as I mentioned, the results just came out. It's something NVIDIA historically has done very well in, and you did very well again. So can you talk about some of the recent results?
Yeah, we're really pleased with the results this round. Most notably, we did our first ever submission with the Blackwell platform, our upcoming platform that's coming to market soon. And the results were really wonderful. We basically came in with performance up to 4x our previous generation on this first Blackwell submission. This is on a per GPU basis. But in addition to the Blackwell entry, beyond just being Blackwell, it was the first ever submission to MLPerf using the FP4 precision. Right. And there are a lot of challenges to using FP4. FP4 in theory is great. So that's for your listeners, FP4 is floating point 4 that's describing each data point using just 4 bits, right? Which is a very small number of bits to try and describe.
Typically, how many are used?
Well, typically it's more on the order of 16, sometimes even 32. Right now, in more recent years, we've been using a lot of what's called FP8, which uses 8 bits, and we've used that selectively for training and then also for inference. Right, FP4 for now, we're really kind of focused more on inference, and this involves a number of techniques around what's called quantization, which is a fancy way of saying rounding, where we are looking to figure out the intelligent ways to use reduced precision while not compromising accuracy. And that's always the tension when you go to use reduced precision is, using fewer bits, which has lots of advantages. I mean, it's less compute load, it's less memory traffic, less pressure on your memory bandwidth. I mean, there's a lot of upside to it, assuming you can preserve accuracy. And that's always the challenge. So we've put together a set of tools we call the Quasar quantization system that help us do that. It includes some of our existing tools, but it also captures a lot of the very recent algorithmic work we've been doing around doing intelligent quantization such that we can use FP4 while meeting all the accuracy targets of MLPerf for the workload we submitted on. In this case, it was Llama 270B, which is a fairly recent large language model that's in the benchmark.
All right. Now, you mentioned the Blackwell platform, and I wanted to pivot to that. I'm glad you said the word platform, because I do think there's some confusion around Blackwell. Typically, when I see it referred to in the media, they talk about it as a chip or a super chip, but it's much more than that. And so can you first talk about Blackwell, the chip, but then Blackwell, the platform?
Sure. And it's a really good distinction that you draw there, because Blackwell ultimately is a platform. But to talk about one of the key components in said platform, which is the GPU, it is an amazing accomplishment by our architects and our engineers, where they've brought together 2 radical limited dies and then fused them into a single GPU connected over a very, very fast interconnect that runs at, I believe, about 11 terabytes per second. So you have this incredibly fast interconnect that lets those 2 GPUs act as one. Right. So that's one of the ways that we've been able to, grow our compute capabilities in Blackwell. It's more than 200 billion transistors, actually. And then, we've added new features, like we talked about just a moment ago, the support for the FP4 precision. We'll also support FP6, which is another reduced precision that developers may want to opt for. And there's a number of other features we're bringing in around confidential computing, around manageability, just a whole set of features. And we've got a really good architectural white paper that walks people through all of these in pretty good detail for those who are interested. Then expanding that out to think about the platform. So that GPU I just described is just the beginning, because ultimately it has to be brought together with a great CPU, and we will offer things like our Grace Blackwell platform, which combines our Grace CPU with 2 Blackwell B200 GPUs in a single package. But it also requires, additional pieces, because if you've heard about kind of what I'd call our flagship product for Blackwell, which is the GB200 NVL72, this product is going to bring together 72 of our Blackwell GPUs, all running and talking to each other over our NVLink fabric. And this is made possible by our NVLink switch chip technology, which is another key component to the overall Blackwell platform. Because ultimately, as these, particularly LLMs, since that's what we've been talking about, continue to grow, one of the increasing components of getting great performance isn't just going to be the compute, it's also going to be the communication. which is the GPUs have to exchange information as they're working on the queries for these very, very large language models. And now we're getting into like trillions of parameters, for instance. And so if you think about how much that overhead comprises in terms of the total execution time, it can start to grow. And so if you have like a point-to-point connection implementation, that's not going to scale as well, right? Whereas if you've got NVL72, you now have 72 GPUs all talking to each other at 1.8 terabytes per second. And most importantly, it's an all-to-all topology, which is to say every GPU can talk to every other GPU directly. It's one hop through NV switch, and you're immediately talking to that other GPU. So this dramatically reduces communication overhead to allow ultimately the performance to not be gated by that communication. So this is a really important innovation that's going to basically be an enabler for that next generation of LLMs that we see coming to market over the next couple of years.
Yeah, the all-to-all architecture is pretty interesting. In fact, you talked about that. I think NVIDIA went deep on that at the recent Hot Chips event, right? So, that's comprised both of NVLink and NV Switch. And so, for those that maybe aren't that familiar, you talk about the difference of both and exactly what does all-to-all mean. I've described it as a fabric. Am I thinking about that right?
You are, yeah, it is. So NVLink is the fabric, right? That can be thought of as the fabric, over which the communication happens. But then again, the key enabler is the NVLink switch chip, right? Which is essentially, the thing that's doing sort of the routing over the NVLink fabric. And again, it allows any one GPU. Say if you've got 72 GPUs, GPU 1 can talk to GPU 72 directly. One hop through NV switch, and those two things are communicating with each other at 1.8 terabytes per second, right? So an incredibly fast rate of connect for those two things to communicate. And for every GPU pair that's communicating, their communication also happens at 1.8 terabytes per second. So there's just an incredible amount of bandwidth that we're bringing to the platform in the form of the Blackwell generation of NVLink switch. Right. And again, we believe that's going to be a necessary component to continue to scale performance because, as I was talking about communication overhead, there's this notion of what's called Amdahl's law, which basically the simple version of it is you're only as fast as your slowest component, right? Which is to say you will be limited by whatever the slowest component is in your system. So to ensure that communication doesn't become the bottleneck, this is why we've designed NVLink switch the way we have. Yeah,
what I've found really impressive about that is all networks, when you think of traditional network technologies, Ethernet, whatever, there's always a little bit of overhead, even with true non-blocking systems, except with NVLink, it seems like you've eliminated virtually all of it, then you truly get line rate. And so the advertised bandwidth is what it is. And so it's the fastest possible connection method. And I think sometimes people forget about the importance of the network when it comes to AI. We focus on the processors and things like that, but I think to your point on Amdahl's law, if your network's slow, you're going to have an awful lot of idle time with those GPUs, and no one wants that, right? So
right, absolutely right. And it also has a role to play on the training side as well, right? Because of course, training also is very communication intensive. As you go through and do the training process, as you run your samples through, the first thing that happens in training actually is inference. You run samples through and you try and do predictions on them or inferences on them. And then you want to check to see, did we get a good answer on that? Or was the answer meeting our quality expectations? And if the answer is yes, you just keep going. If the answer is no, ultimately you then have to do what's called a back propagation to update all the weights in the model to correct for the error that just occurred, right? And when you do that, that involves basically what's called either an all gather or all reduce or some combination of those two things, which essentially is every GPU having to communicate with every other GPU to do the update on those weights in the model. And so that's a lot of communication. And this is another place where NVLink and NVL72 will have a critical role to play in training those large language models to bring them to market.
Yeah, Dave, I wanted to talk about last topic is NVIDIA, the software company. In fact, in preparing for this, you reminded me that there's twice as many software engineers at NVIDIA than hardware, even though you're largely characterized as a silicon or a hardware company. The latest software innovation out of NVIDIA is something called a NIM, and specifically NIM blueprints. And so could you talk about what NIMs are and then what the relationship to NIM blueprints is?
Sure. So yeah, Nims is kind of an important addition to the overall set of software we offer to our developers. We've been on a kind of an ongoing sort of journey here to bring better, easier to use software to the development community. So it started with what's called NVIDIA AI Enterprise, and we publish containerized software to the community on about a monthly cadence, right? And basically all of our software tools are made available to the community essentially for free, many of which are open source. But the most recent edition, NIM, takes inference software or inference models, I should say, and containerizes those in a way that makes them, almost turnkey, easy to use is the goal, right? While we talk a lot about performance in the AI world, a less talked about topic is ease of use, right? AI is still a hard thing to do, and LLM AI, LLM focused AI, I should say, is sometimes is even harder to do. So one of the goals of NIM is to not only bring great performance to the industry, and our NIM containers are essentially delivering the equivalent of bare metal performance. So the performance is definitely there, but the other goal is to make it easier to deploy. And so and what we do is we try to have either day zero or very close to day zero support for every new prominent community model that comes to market. The most recent example being Llama 3.1. And that comes in a couple of different sizes, up to 405 billion parameters, right? Now, what we've done is we've taken NIM a step further with NIM Blueprint, where we want to focus on very specific use cases and build out an even more complete solution for those particular use cases. One of them, for instance, being healthcare and drug discovery, right? To make it even easier for those organizations working in that field to take advantage of sort of the power of LLMs, the power of inference and AI to accelerate their work. And in this case, speed time to market for critical drugs and medicines, which can help attack and fight illnesses, right? So the work that we're doing here, again, is not just about, of course, we want to have great performance because great performance translates into a better cost structure for our customers ultimately, right? But part of that as well, not just the performance, but ease of use is another thing that can help reduce time to market because there's less time spent developing and sort of troubleshooting or trying to learn how to use something, as opposed to a lot of that hard work has already been done, and that allows them to get to market faster and realize returns on their investment.
Yeah. Now let's broaden the software topic too, because it's interesting that NVIDIA, by all accounts, is the market leader in GPUs. I don't think anybody would disagree with that. And it's interesting that I often see, on the financial news or whatever, competitor A is building a new GPU and competitor B is building a new GPU, and they wonder if that's going to threaten NVIDIA. And I've always thought that the moat around you is actually your software itself, right? Not the GPU, because trying to maintain performance leadership in one specific aspect of your business through all moments in time is difficult. And so talk to me about the overall NVIDIA software strategy and how you think about that as a way to not just create differentiation for your company, but to make your customers' jobs easier.
Sure. Well, I mean, it sort of maps back to, NIM is a great example of that, for instance. We realized early on, and this is going back like literally 10 years when deep learning first kind of got going. It really first got going in about 2012 with AlexNet, and the ImageNet competition is what we kind of called the big boom of deep learning, right? But we realized early on that software enabling was going to be a critical component to making AI successful in the market. Because if you think about it, AI is not really a new topic in the field of computer science. It's actually been around for decades and decades, really going all the way back to, even Alan Turing, right, in the 1940s. Yeah. With that said, it's kind of come in and out of fashion. And it wasn't until we got to deep learning and were able to really start making these networks much more intelligent, much more accurate, that suddenly the aha moment happened around, my God, we've got, so many companies around the world and organizations around the world have all this data from which a lot of times they're drawing very little insight, and deep learning can help them unlock many, many more types of insight and build whole new classes of applications. So as we think about the software to enable that, it really comes down to some degree, I will say in some cases, meeting the data where it is, because, data movement ultimately is something you want to minimize to get great performance. And this is where things like, cloud computing has a huge role to play with a lot of our customers, because a lot of their data already lives in the cloud, because cloud computing has also been around for quite some time. And so as we continue to build out our software, we're always looking at, where we think the market's going, and trying to build the solutions for our customers to help them realize the benefits of these new discoveries. Because the other great thing that's so exciting about deep learning and AI is the amount of innovation and experimentation that we're seeing and the rate at which we're learning new things. So there's also just the ongoing challenge of enabling an ecosystem and building a platform that is both sufficiently that's performant, versatile, but also flexible enough such that they can continue to do sort of their experimentation, so that we're not just the platform of choice, we're also the laboratory of choice, right? So that as that next wave of innovation comes, we want those innovations happening on our platform. So a lot of the software work we do is about creating that place where developers can come and try new things, see what works, and bring those innovations to market.
Yeah, what I've always liked about your software strategy, it enables you to go vertical too, right? So you've got, Drive for automotive and Clara for healthcare and things like that. And so while you've built different form factor hardware for those, the software is equally important. I've always thought that was a very interesting way to go to market. Typically, when I see vertical industry strategy, it's like Salesforce, right? It has health, but you don't often see that down at the hardware level. So, anyways, anything else you want to add?
No, I mean, I think we've covered a lot of topics.
Yeah.
I think I'm really excited to see Blackwell come to market. I'm even more excited to see what companies and organizations are going to do with it, because again, it's going to unlock a whole nother level of performance that the industry has never even seen. And I think the scalability of NVLink and NVLink switch, being able to take that out to 72 GPUs, the amount of additional performance we're bringing in the Blackwell GPU architecture, and then more broadly, the Blackwell platform architecture, I think is going to really enable some pretty amazing stuff that we're going to see in the next year or two.
Yeah, well, I'm looking forward to seeing what Blackwell enables, because I'm expecting to take all this great AI innovation to an entirely another level, and so almost science fiction like in some cases. All right, Dave. Well, certainly appreciate the update, and hope to have you back again sometime soon. But on behalf of Dave Salvator from NVIDIA, I'm Zeus Caravallo from ZK Research, and thanks for watching. Make sure you hit the subscribe button, and I'll see you next time on the next episode of ZKast.